Despite our progress with the domain model, we still have some missing requirements left. First, we need to check if the price of the snack the user is buying is equal to or less than the money they inserted. We shouldn't allow the purchase if it's not the case. Similarly, we must check if there are any snacks left in the slot. Next, we need to return the change back if the user inserts more money than needed. And finally, we shouldn't allow the purchase if there is not enough change in the machine to give the user back. Let's start with the first two requirements, as they are pretty simple to implement. I'm adding a test that verifies we cannot make a purchase if there are no snacks in the slot. You can see it just creates an empty snack machine and tries to buy a snack from the first slot. It should fail because at this point there are no snacks inside the machine yet. Note that the test is passing. That's because in this method we try to create a snack pile by decrementing the quantity of the already existing pile, which essentially gives us a negative number. This number then doesn't pass this check, the constructor throws an exception, so we already have the behavior we need. Let's comment these lines out just to make sure the test works. The unit test does indicate a failure, very good. The second test we need to add is the one that verifies that we cannot make a purchase if there is not enough money inserted. So basically what the test does is it loads a snack with the price $2, inserts $1, and tries to buy that snack. The test fails because right now nothing prevents us from buying a snack even if we don't have enough money in transaction. Let's fix that. So if the price of the snack in the slot is more than the amount of money in transaction, then we throw an exception. The test passes, perfect. The next requirement is not as simple as it might seem. We need to make sure the machine returns change, so basically what we need to do is we need to add to the money inside only those money that is worth the snack price, not more. Right now we just move all inserted money to the money inside, regardless of the snack price. This seemingly simple task raises an important question. What exact set of coins should we transfer? For example, what if a user inserts 4 quarters and $1 bill and tries to buy a snack with the price $1? Should we transfer quarters or should it be $1 bill instead? Or maybe it doesn't matter. As always, when we encounter an edge case we didn't think of, we need to go to the domain expert and ask her about the expected behavior. It turns out that this question is more complex than we initially thought, and we have to add another business rule to our requirements. That is, the snack machine must try to retain coins and notes of as little denomination as possible. So in the example above, the machine needs to appropriate 4 quarters and return the user $1 bill. That makes sense because otherwise the machine will run out of change very quickly and won't be able to serve clients who don't have the exact amount of money in hand to make a purchase. It also means that when a user inserts, for example, 4 quarters and asks to return the money back, the machine must try to return $1 bill instead and keep the quarters. Alright, let's start with a new test for the return money method. The snack machine should return the money of the highest denomination first. We need a separate method for this test, load money. We will use it to load some initial money into the machine, just as we do with load snacks. So here we load $1, try to insert 4 quarters, and return money. The return method should be implemented in such a way that allows the machine to keep the quarters and give the user $1 instead. So the number of quarters inside the machine should be 4, and the number of $1 bills should be 0. Implementing the load money method, it just adds the money to the money inside. Let's look at the current implementation of the snack machine class. Note that we have two separate value objects to represent the money inside the machine and the money inserted by a user. We know now that we don't have to distinguish them because it may be that the machine returns to the user not the exact same money they inserted, but the equivalent amount from the money inside. Do we need two separate value objects in this case? We don't. We can just keep all money, be it money inside or money in transaction, in a single property and track the amount the user inserted using a simple numeric variable. So I can change the type of this property from money to decimal. That would be that variable. The money inside property will hold all money in the machine, regardless of how they got there. I need to fix the code. Here, instead of placing the inserted coin or note to the money in transaction property, we need to just increase the amount and put the money directly to the money inside property. Fixing other occurrences. In the buy snack method, we don't need to transfer the money from one property to the other, they are already there. So all we need to do here is nullify the money in transaction. This method still works incorrectly, of course, but we'll get back to it later. Changing the tests so that we use the decimal type instead of money. In the view model, there is also no need to sum the two instances, we can just use the first one. Perfect, the code compiles now. The test still fails, however, so we need to change the return money method. To make it work, we need to somehow allocate a required sum from the money inside and subtract it from the overall amount. So basically what we need here is something like this. Allocate the money in transaction amount, which would be the money to return, and subtract it from the money inside. This allocate method will handle all the logic of deducting coins and notes of the highest denomination. I'll just copy the implementation here, but keep in mind that this is definitely something that needs to be covered by unit tests, which I'm leaving as an exercise. You can see we start from the most valuable notes and try to fill the required sum with them first, and then fall down to less valuable bills and coins. After that, we return the resulting money object. Good, the test is passing. The second piece of functionality we need to implement is returning change after a purchase is completed. So here I load a snack with a $half price and also load $1 using 10-cent coins. After I insert a dollar and buy a snack, the amount of money inside should be $1.50, which means that the machine should take the dollar and give 50 cents back. The test is failing, you can see the snack machine takes all the inserted money currently. One little thing to make our code more readable. We can introduce an additional multiplication method in the money class and implement it like this. Basically multiply all members by the multiplier. Now instead of using the money constructor, we can write 10 cent multiplied by 10. Much better. To make the unit test pass, we need to allocate the difference between the inserted money and the price of the snack and subtract it from the money inside. The last use case we have to take into account is when the machine doesn't have enough change. You can see the snack costs $half, but we insert a whole dollar here. That should result in an exception. To make it work, we need to check if the change we're allocating is indeed sufficient. If it's not, the method has to fail. Very good, we implemented all required functionality. In the previous demo, you saw how a new requirement we didn't think of emerged. There almost always will be requirements which you miss initially and which you discover as you progress with your software. It is typical in any more or less complex project. Don't hesitate to refactor your domain model in such situations to make it better convey the new knowledge you unfold. It is important to closely collaborate with the domain experts on the new information and try to refine the domain model together. In our case, the new requirement led to the situation where we don't have to distinguish the money inside the machine from the money in transaction. It is easier to treat them as a single value object and just track the amount of money inserted by the user with the decimal property. In this module, we talked about aggregates. That is a design pattern that stands for gathering multiple entities under a single abstraction. There are several attributes that belong to aggregates. First, an aggregate is a conceptual whole, meaning that they represent a cohesive notion of the domain model. Every aggregate has a set of invariants which it maintains during its lifetime. Second, every aggregate should have a root entity, the root entry which can be used by other aggregates. All entities and value objects outside a given aggregate should work with it only via its root entity. Third, aggregates act as a single operational unit for the application layer. It means that the application code should work with whole aggregates, not with separate entities in it. And finally, aggregates hold consistency boundaries. They should be stored to the database within a single transaction. We talked about how to find proper boundaries for aggregates in your domain model. The best way to do this is to answer the question whether or not an entity makes sense as a separate concept. If so, it should be the root of its own aggregate. It's a good idea not to expose internal entities outside of the aggregate boundaries, because it helps maintain proper encapsulation. It's not always possible, but in many cases it is. And finally, you saw an example of refactoring the domain model after revealing a hidden requirement. Remember, there always will be things that you cannot foresee upfront. It's important to iteratively evolve your domain model after the knowledge you get about the problem you are working on. Alright, that's it for this module. In the next one, we will talk about repositories and their connection with aggregates.